we're going to start work on the rocket project, which will be a multi-stage project. And we're going to start with, it's all about simulating the launch of a rocket. And we will gradually add more complicated, more realistic, and thus more complicated assumptions. But we're going to start with a really simplified version of a water rocket. We'll assume constant mass and thrust, and we'll work through this example and get the basic simulation working. And then once that basic simulation's working, we can go through each iteration, making it more complicated. So to start with, we're going to need some variables. We have up here, we have gravity of negative 9.8 meters per second. We should probably put that in there. Of meters per second. Thrust of the rocket in newtons. Mass of the rocket in kilograms. The amount of fuel. The burn rate of the fuel. In fuel that's used per second. The time step of the simulation. So we're going to simulate this in tenth of a second intervals. So a pretty granular simulation. And then the launch angle is going to be 90 degrees. So we're just going to assume a straight up launch. And to do the simulation, we're going to be recording the velocity, the altitude, and the time at each stage of the simulation. So when we start, it's time 0, altitude 0, velocity 0. The rocket's not moving, it's on the ground. And we want to then make this more complicated. So we need to have a loop. And that loop is going to run through each stage of the rockets. It's going to run through step by step the rocket's flight as it flies up in the air and the fuel runs out and then it crashes back down to the earth. And at each stage, the velocity of the rocket's going to be based on its current velocity and then the acceleration applied to it by thrust and by gravity. We're going to use the velocity to get the altitude, which will be based on, the previous altitude plus how fast it's going times the time step, and then we'll increment the time step. So I actually have this, come over here and grab this loop here, and we'll come back to this part. We'll paste this in. I'll push the rest of this down off the screen for a bit. I want to walk through what we're doing here. We set a variable I to 1, and that's going to be just the index variable for all of our arrays. So we're going to say, we're going to run this while the altitude is greater than or equal to 0. We do that or equal to, so that it runs. Otherwise, it starts just above the ground, and it wouldn't run at all. So we're going to say, while the altitude is greater than or equal to 0, keep running. So it's going to keep going until the rocket hits the ground and plows a little bit into the ground as it crashes. And the change in velocity is going to be based on whether or not there's any fuel left. So as long as we still have some fuel, then the velocity at step I plus 1 is going to be, the velocity at the next step will be the current velocity plus thrust divided by mass plus the effective gravity times the time step, right? It's always going to be times the time step because, if it's going, if the acceleration is a thrust upward of 50 newtons and divided by the mass of 2, so 25 meters per second upward minus 9.8 meters per second downward. That acceleration, the change in velocity, if it's per second, you got to multiply it by the 0.01 time step to see how much velocity changes over a tenth of a second. If the fuel has burned out, been used up, so there's no more fuel, then the velocity at I plus 1 is just going to be the current velocity plus the effective gravity. Then once we have that velocity, we're going to look at the change in velocity between the two time steps. If you go from 15 meters per second to 16 meters per second, then it's an average of 15.5 meters per second over the time interval. And we use that average velocity then. We take the altitude at time, for the next altitude is going to be the current altitude, plus the average velocity times the time step. And then we increment the timer. We add whatever the time step is to the previous timer to get the next value. And don't forget to burn some of the fuel. And then we increment the index variable. So again, if we look at this, just breaking these up, this if-else statement here is computing the new velocity based on the old velocity, and we have to know, is it still thrusting? When there's still fuel, you're going to have the velocity is going to be changed both by the thrust and by gravity. After the fuel is gone, it's just going to be gravity changing the velocity. Then we compute the average velocity. We use the average velocity to find how much the altitude changes and record the new altitude. We add the time step to the previous timer to get the next timer value, and then we use up some of the fuel and increment I. Then afterwards, we want to look at some values that we get from this. So we'll get the maximum velocity and the maximum altitude, and we're going to plot the altitude against time. So let's save this and run it and see what we get. You see here, it gets to a maximum velocity of 456 meters per second, a maximum altitude of 17,449 meters. And here's the chart or the plot of the altitude. It's accelerating steeply, and then in here, and then the fuel runs out after 30 seconds, right about here. And then it just follows a ballistic arc as it goes up, and gravity is slowing it down, and then it comes crashing back down. So that's take zero. And this is take zero. It's assuming a straight up launch angle, and so there's only velocity in the y direction, or altitude and velocity in the y direction. And it's, the most simple we can make this rocket project. In successive simulations, the next one, we're going to look at what happens if we have an x and a y component to velocity, because rockets don't always launch straight up in the air. And then we will move to a NASA-sized rocket, so a realistically sized rocket, and we're going to have the fuel and a realistic sized thrust, and we're going to have the fuel burn up over time. So as the fuel burns, the mass gets smaller, and the rocket, consequently the thrust changes the velocity more. But this is take zero of the rocket project.